Okay. Hey everybody, sorry for being late. I just drove as fast as I could. Uh, but I'm here. Any questions before we get started? Good. All right. So last time, oops, making this full screen. Perfect. 1, 2, 3. Okay, and it's recording, and we're good. I think we're recording. Let me see. Uh, yes, we are recording. Okay. All right. So the last thing we were talking about was memory type instructions. If you remember, I said that we have load and store as the main two things that we are looking at for memory instructions. And then we have various different versions of that, including like whether we are reading 32 bits, which is we call word. If we do 2 bytes, which is half word, or we are just reading a byte, which is byte. And then whether we are doing it signed or unsigned, and that will give us this kind of table here that almost all of them has very similar format. The only difference is how large the data and how we read or write the data. So you should kind of pay attention to this part of the system. Another big thing that I often see people are kind of confused about is store has two sources, okay? So both of these are inputs, okay? Both of them are like, pay attention that it's like RS1 and RS2 versus for load, this is different, right? So for load, this is RD and this is RS, right? So notice the difference between these two guys, right? For load, the RD is the destination register. In other words, it's the output of the system. So we read things from the memory and write it to the register. Versus for store, we are reading it from that register RS2 and write it to the memory. That's why this is source register. That one is destination register. But if you look at the kind of syntax, this is like this. So x2, let's say, like 4x0. And then we have SB, which is also x2 for x0. Here, this is source, but this is destination, okay? So that's the important one. So the difference, like they look very similar, but they're not the same, all right? So we talked about arithmetic and we talked about memory. Let's also talk about control flow. So control flow is, if you remember, I told you that we are doing store program machines, which essentially what we have is sequence of instructions that are stored in the memory. Each line is kind of one instruction. And then the CPU kind of like go and grab each one of these instructions one by one, and like first read this one, bring it, execute it, and then go bring this one, execute it, and so on and so forth, okay? In order to keep track of like which one we were executing, we usually have this internal register inside the CPU called PC. This is different register than this general purpose registers that we talked about. This like X0 to X31, these are what we call general purpose registers. PC is another register, which is different than these 32 registers. And all it does is kind of pointing to the current instruction that we are executing, okay? So this is how we kind of keep track of the program and we execute this. In regular systems, we assume that memory is linear, as I told you. So we kind of like do one after another, okay? So if nothing happens, we just do the first instruction, then the second instruction, the third instruction, and so on and so forth. So we kind of linearly go down to execute instructions one after another, okay? And then typically, as a result, next PC is always PC plus 4. Why is it 4? Anyone? Why next PC is not PC plus 1? Is it PC plus 4? Yeah. Exactly. So remember I told you that each line in the memory is 1 byte. and our instructions are 32-bit. So essentially, each instruction is 4 byte. In other words, each instruction is 4 consecutive lines. So if I read the first instruction, which is the beginning of here, the next instruction is 4 addresses down, okay? Because we read 4 bytes together, and that's one instruction. The next instruction is the next 4 bytes. So we have to do PC plus 4, okay? So in our 32-bit version, everything is PC plus 4. If our instruction size was like 16, this would have been PC plus 2, right? Or if it was like 64, this would have been PC plus 8, and so on and so forth, right? But in our 32-bit version, next PC is always PC plus 4. Anybody clear? Anyone has any question why? Yeah. Say it again. Yeah, so the question is it PC plus 4 bytes? So remember, this is address, okay? So PC is an address, okay? So if it's pointing to this address in the memory, wherever it is, okay, the next instruction should be 4 lines down from here, okay? And then remember why? Because every line is 1 byte, and we want to go 4 bytes down. All right. So next PC in regular systems is always PC plus 4. So essentially the system is like this, that we read the instruction, execute it, do PC plus 4, go read the next one, do another PC plus 4, next one, next one, next one, and so on and so forth, okay? But then we will have what we call control flow instructions. The reason that we have control flow instructions is that not all the time our program are linear. Why? For example, take a look at this example, right? Like we have things like if then else's, that if, for example, x is equal to y, we do something. If x is not equal to y, we do something else. And then afterwards, we do something else, right? So if we are actually plotting what we call the control flow graph of this, this is called CFG. So we have a block of code A. So there's kind of a bunch of instructions here, and this is this block. Then we have kind of like a fork, a divergence, that if x is equal to y, we're going to run one block. Let's say this block here. It could be many instructions here. I don't know how many. Or it could be an else kind of block that we run a bunch of other instructions here. And both of them kind of merge at some point back into kind of a linear, right? And then if you think about this in terms of instruction memory, remember I told you that instruction memory is kind of like sequence of instructions. Now we need to decide where we're going to put these instructions, right? So for example, one way of doing this is that I put all the A-related instructions here. But then at this point, I either need to put B or C, right? So let's say I put C. So I put C instructions here, and then I put B instructions here, and I put D instructions here, okay? In this case, when I reach to this instruction, which is this if equal x is equal to y, then I need to decide that whether I want to continue with C. So if I do PC plus 4, I start executing C. But if I, for example, if x is equal to y, I need to skip C and I need to run B, right? This means that I need to somehow change my PC from pointing to here to pointing to here, okay? This is what we call a control flow instruction, which what it does is changing the PC, right? Where it changed to, it's the beginning of the next block, right? So we need to know where we jump, but we need to somehow, instead of doing PC plus 4, doing something else. We need to replace PC with that target address, okay? This is what we call control flow instructions. And again, it doesn't matter whether we had B here. So we could have, for example, had B here and C here. In that case, for example, if the jump was taken, if the branch was taken, we just continue normally. But at this point, we had to jump over, right? Once it's done, once we run B, now we need to run D. We need to skip over C. So we need to again jump. So you cannot eliminate the jump. You always need to jump. It's just a question of where you're going to jump to. Okay? Questions? Cool. So how do we do that? So first of all, what are the cases that we have jumps? Like, why do we need jumps and branches? Anyone? So I already gave you one, if then else's. Anything else? Yeah. Loops? Uh-huh. Anything else? Yeah. Case statements? recursion, function calls, and then recursions would be like a specific case of that. Anything else? Yeah, pretty much you said all of them. So we have usually a checking condition. So if then else's, switch cases, all that is conditions. Then we have various different loops, loop, for loop, while loop, and so on and so forth. Then we have function calls and function returns. Returns are also the same thing. And then you can have like recursion, or you can have just a regular. And then we have exceptions and interrupt. So some form of an error happens. If the operating system needs to take over and all those things, that's also some form of a jump. Okay, so these kind of 4 different types of control flow instructions we have in any ISAs, including RISC-V ISA. Okay. So generally for jump, the big thing is that when we are jumping, we need to know where we're going to jump to, right? So we usually call that destination address. All right. How do we calculate that destination address? We use PC relative addressing, which means that we don't necessarily need to know the exact address. We just need to know how far from PC we need to jump, okay? And the important thing about jump is that you can jump forward or you can jump backward, right? So both of them can happen. So for example, for loops, you kind of like do this, this, this. At this point, you go back and continue doing that. So that's why you have this loop behavior, right? So you can jump to the older PC addresses. Or you can move forward. You can jump forward if you, for example, have a function call, right? Or if you have a switch case, or if you have an if then else. So you have both what we call backward jumps and forward jumps, right? In both cases, what you do is that you add some offset to the PC, okay? If this offset is a positive number, then you jump forward. If this offset is a negative number, you jump backward, okay? So think about it similar to the immediates, and that's why immediates are very important for us. In like regular CPU, like ALU operations, we were like adding a register to a negative number. For control flow instruction, instead of adding a register, now you have PC, and then instead of like immediates, you have an offset. Okay? Question? So the question is, what's the motivation of not doing the entire instead of like doing offset? You can do entire as well, and in some cases you can. But what I'm saying is that usually you add something to the PC to jump. So whether you can say that, okay, I'm gonna like compute the. So when you're computing the address, you have the destination address, you have the current address. You need to basically compute this offset and add that offset to your PC. That's how you compute this number. Yeah. Good question. Can we jump to a misaligned address? So remember I told you that you kind of like have to be multiple of 4, right? So technically, since I have an offset, I can have like an offset somewhere in the middle. Some ISAs allow it. Most ISA don't. So it's kind of throw an error if you just jump. Another thing that I'm going to show you is that we're going to actually prevent this from happening. So what we're going to do is that we're not going to let offset to be not multiple of 4. So we're going to actually shift it in hardware ourselves to make sure that it's always multiple of 4. Yeah. So the question is, how do we enforce that we are not jumping somewhere in the middle? And that enforcement would be in hardware. Think about that. If I always shift my offset by 2-bit to the left, I always guarantee that this value would be divisible by 4, right? So what I'm going to do is that whatever offset that you provide, I'm going to first shift it by 2 and then add it. So then you can be like, you can always make sure that you can use any offset that you want. In hardware, we always make sure that it's always divisible by 4. Does that make sense? Actually, next week we will show you how we do it in hardware. Yeah. Mm-hmm. The question is, if I want to jump to an absolute address, what I do. So let me actually show you the instructions, and then you will see how it works. So hold that thought for a minute, and I'll show you how. All right. Before jumping to answering that question, there's also an important difference between what we call jumps and branch. Okay, jumps always change the PC, so there is no like condition around it. Branches, there is a check. For example, we branch if these two values are equal. We branch if this value is greater than the other value, right? So there is some form of a condition, some form of a check going on. If the check is true, then we jump. If the check is not true, we just continue normally. We do PC plus 4, okay? So the difference between what we call jump instruction versus branch instruction is both of them are quote unquote control flow instructions. The difference is that jump is always jumping, changing the PC, but branch is kind of a check and then changing the PC, okay? Another thing that RISC-V particularly has is this notion called link. So link is this additional activity in addition to jumping, is that we remember the address that we jumped from, okay? So let's say, for example, my current address is 100, and I have this instruction. For now, I'm going to call it jump, but there's actually another thing for it. And let's say we want to jump to some label, okay? And this label is somewhere else. So let's say the label is stored at address 200, and this label is some other instruction. Let's say, I don't know, add x2, x1, and x0, okay? So what this instruction does is that PC at this moment is equal to 100, okay? And by the way, I'm just showing these numbers in decimal, but you can use it like hags or whatever. At this point, what is going to happen is that this instruction I'm going to show you later basically going to change PC to 200, okay? I'm going to show you the mechanics of it, but for now, let's assume that this magically happens, okay? And then at this point, we're going to, so since the next instruction is now pointing to PC 200, then we're going to start executing this instruction. I'm going to continue, okay? So linking is basically saying that not only I change PC to 200, I'm going to also provide another register here, let's say x1. And what I'm going to store in x1 is the current value of PC plus 4. So in other words, x1 will be equal to 104, okay? So this process is called linking, which means that we're going to remember the address that we jumped from, plus 4, which is kind of pointing to the next instruction. The reason for this is that now at any point here, I can just jump to the address that is pointing in, let's say, x1, and this will immediately going to put me back to the right next instruction after this. So it's very convenient, especially if you think about like return instruction. What return does is that if this is a function call, you're going to go and write. So this is, for example, like, there's some instructions and there is a call foo. So we're going to actually, at this point, we're going to just go and run the foo function. And at some point, we're going to return. Where should we return to? We should return to the next instruction here, right? Whatever it is. So this linking essentially going to remember that address. It's going to be always stored in the register that you provide. And I'm going to show you the syntax later. But then next, you always know that this address is always pointing to the address after the jump. Okay? Yeah. You can use any other. So the question is, which register should I use? You can use any register. Yeah. Yeah, so the question is, what if, for example, you overwrite the link? You can. So it's a bug in your code. So if you actually, you have to be careful about, where you store it and not overwrite it. That's why there is some conventions that I'm going to actually talk about, hopefully this lecture, about like call and return. So we typically have like a dedicated register, which is actually x1, by the way, that is always for storing the return address. And you don't want to overwrite that. If you want to overwrite that, you have to save it. You have to push it into the stack, overwrite it, but then you have to recover it from the stack and then return it. Otherwise, you're cooked. Yeah. Yes, this is still an operand. So this is an operand to this jump instruction. All right. And then what if we don't link? So not necessarily all the jumps really need linking, okay? In that case, you have two options. You can just do jump without linking, Or there's another option that you can link to x0, okay? If I link the address to x0, nothing happens, right? Because remember, you cannot overwrite x0. So you'll see lots of times that you have jump and link to x0, which means that we don't care about the linking address, okay? So here's the syntax. So we have what we call JAL, JAL, and JAL-R. These are our jump instructions. It stands for jump and link, and this one is jump and link register. The syntax is like this. So we have JAL, RD, and label. Okay. So essentially, the instruction will look like something like JAL, X10, and label. I don't know, whatever label you want to use. Okay. And this label is an absolute address. It's a matter of convenience. Instead of computing the distance and the offset, you provide the actual address. The actual syntax of JAL is something like this. And offset. Sorry, immediate, basically. So RD and immediate. In other words, when you're actually writing the binary of this, you have to provide the immediate. But the nice thing about compiler is that you can provide the label, and the label will compute the offset for you, okay? So actually, I'm writing this here. So essentially, your label is equal to PC plus the immediate, okay? So you can either provide the immediate, the number, and it will basically do PC plus that immediate and provide you the label. Or if you don't feel like computing that, you can just provide the label, okay? For example, in your homework, I'm going to ask you to do it both ways. So provide the label and provide the offset and see what's the difference between them, okay? For JAL-R, you don't have the option for the label. You have to actually provide the offset, okay? And what's the difference between JAL and JAL-R? The difference between JAL and JAL-R is that JAL always assumes that this is PC relative. So the offset is always added to PC, okay? But what if I don't want to use PC? What if I want to use another register as my base? That's where you're going to use JAL-R. So in JAL-R, you're going to have something like this. So you're going to have, oops. So you're going to have JAL-R X10, then X1, for example, and let's say some numbers like 12, okay? So what does this do is it adds whatever value that's stored in X1 with 12, and it's going to jump to that address, okay? So if your X1 is 0, it's going to jump to address 12. If your X1 is 100, it's going to jump to address 100 plus 12, 112, and so on and so forth. JAL doesn't have this. JAL is like this, X12, X10, and 12. This means that whatever address that I'm currently at, I'm going to add 12 to it, okay? So the difference is that the base for JAL-R is whatever register that you provide versus the base for JAL is PC, okay? But in both cases, we have this X10, which is the RD, which is the linking address. So in both cases, we link to X10. But what you link in this case is PC plus 4, and in this case is also PC plus 4, okay? But the destination address here is whatever address that is stored in X1 plus 12. For the above one, it would be whatever address is stored in PC plus 12, okay? Questions? Yeah. So the question is, what is a label? If you have written some assembly language, so you have like things like this, and then you have like label, whatever label you want to call it, like label 1, and then do various things. And then you have another label, let's say another, and then you do a bunch of things. And then you have another label, let's say PJ, and then you have a bunch of things. And then what you can do is that, for example, here, if I want to jump, I can say JAL X0, and PJ, which means that once I get to this point, I'm going to jump here, okay? So it's a convenience for understanding how your assembly code works. But another thing that you can do is that if you don't have these labels, and if I want to jump to this address, what I need to do is that I need to see which address is this I need to count. So for example, say that, okay, this is 1 instruction, 2 instruction, 3 instruction, 4 instruction, 5th instruction. So I need to jump to the 5th instruction. And remember, address are bytes, so you need to do 5 times 4. So you need to jump 20 points to get to that label, right? So the offset in this case, for example, is 20. Or you can just provide PJ and jump to PJ. Yeah. So the question is, what's the purpose of X0? So remember that RISC-V doesn't like to have like regular jumps. So either it's JAL or JAL-R. So we always have this linking process here. But if I don't care about the link, I provide X0. So it means that I ignore the link. Does that make sense? So I'm basically linking but not saving the address. I'm just ignoring the address. Yeah. Good question. So the question is, what if the address that you want to jump to is too far? That's why you actually use JAL-R. Because in JAL-R, you can have the base that is itself is 32 bits. So you can actually first load an immediate to your base, the very large immediate, and then jump to that address. But there is a limit to it, right? So you can jump as much as 32, 2 to the power of 32 plus the immediate. So there's actually, you can compute how far you can jump. So in that case, you have to jump twice, for example, if you want to go really far. Yeah. This one, you're asking about this. That's next slide. I'll go into it. Another question. Yeah. What's the purpose of linking? It's to remember the address we jumped from so they can go back to it. If we need to. Sometimes we don't need to. That's why we ignore it. Yeah. Correct. So the question is that if I use X0, I'm kind of ignoring the linking part. If I use any other register, I store the PC plus 4 into that register. Yeah. Mm-hmm. JAL what? Uh-huh. So you have to so the question is, what does the JAL look like without specific offset? So you have to, so you either have like this. So you either have, let's say, JAL, X0, and label, let's say another. Or you have JAL, X0, and some number, let's say 100. Which means that PC plus 100 is the destination address in this case. In this case, we don't know what is the destination address. We just know that this is the label. So the compiler is actually going to generate that number for you. So it's convenience. All right. So in addition to JAL, we also have branches. We have 6 different branches in RISC-V. So we have branch equal, branch not equal, branch less than, branch greater than, branch less than equal, unsigned, and greater equal, unsigned. Okay? And then what they do is that RS1 and RS2 in this case are sources. So it compares the two from each other. Okay? And if it's true, then it jumps to the label. Okay? So in this case, if branch is equal, it will jump to the label. What if it doesn't want, what if the condition is not true? If the condition is not true, then continue normally, which means that PC is equal to PC plus 4. So basically what branch does is that they change the PC value. Either your PC would be PC plus 4, which is the normal way of doing things, or if the condition is true, then it will jump to that address, which is the label. Okay? And then same story with others. So not equal is not equal. Less than is a signed comparison between RS1 and RS2. Pay attention to the order as well. Greater equal is RS1 and RS2 again this way, signed. Then you have the unsigned version as well, which is just measure the, compare the values, the absolute values rather than their signed version. Okay? So you have the less than unsigned and greater equal unsigned. Okay? All right, so the question that one of your students, one of your classmates asked that, why do we have this here? And essentially what we are doing is that we are shifting the offset by 1 bit to the left. Remember I told you that I don't want to have misaligned jumps, right? So I don't want to jump in the middle, okay? And I told you that in 32-bit, if it's 4 bytes, I want to make sure that the offset should be equivalent of 4. So like it should be divisible by 4, right? So I technically should have shifted by 2 bits here. So not 0, just 1 bit. I should have done 2 bit. The reason that I'm doing 1 bit is that RISC-V has this 16-bit version as well. This is called compressed. So it's technically possible to jump to multiple of 2 instead of multiple of 4. So by default, we can jump in the middle of an instruction too, okay? Because there is compressed instructions that you can use. In this class, we're not going to talk about this. So all the instructions are 4-bit, but in hardware, we're going to just shift by 1 bit. So we're going to only jump to even addresses. But technically, if you jump to the middle of an instruction, if your instructions are 4-byte, that will cause an issue. So you're going to have a bug in your system. So you have to be careful about that. Okay? Yeah. Uh-huh. So again, so the question is, if it's everything is multiple of 4, why do we do even? Because there are some instructions that we don't talk about that are 2 bytes. Okay? So again, in this class, everything is 4 bytes, so this seems to be a little bit weird because we are jumping to even addresses. We should have jumped into divisible of 4, but what I'm saying is that there are instructions in actual RISC-V that are 2 bits, 2 bytes, which we're not going to talk about. Yes? The branch instruction does not require linking, so they don't support linking. Because we don't have space. Because we have already, so notice the difference is that in this one we have like operand space, but in this one we don't. So you have to actually linking the other ways. Yeah, you had a question there. You no longer have a question? Okay.
It's like it's to modify the PC register, like you can't load it.
No. So the question is there any way that I can directly write to PC? And the answer is no. These are the only ways that you cannot directly access PC in any way other than this. Any other questions? Yeah. No. Ah. So the question is, how do you preserve branch instructions? Yeah, so for example, you can do this. Like the very weird thing that you can do is that you can JAL X, for example, 1, and let's say PJ, and PJ is your next instruction. So this way you can save the address to. So you don't do anything, you just jump to the next instruction, which you would normally do, but you just save that. Or you can jump to the next one and have a dummy instruction here. So there are these tricks that you can use. Yeah. So yeah, when we are using, so the question is about label. When we provide the label, it's a name, okay? So it's literally like a character or word. When we provide that, you should have a matching label in your program somewhere. If you don't, that will lead into compiler. If you have a matching label, the compiler is going to automatically find that. It computes the difference between the addresses and replace your label with the offset, okay? So label is a convenience for the programmer to that instead of like computing all the addresses, because that's a very tedious process, you just provide the label, compiler will do it for you. But you can also provide the immediate yourself. So for example, say that, okay, I want to jump 24 lines. You can do that too, okay? That's actually what happens in the hardware itself. So Hardware does not understand labels. It only understands addresses and addition of addresses. So what it will be translated into is the actual offset. You can provide the offset yourself, or you can provide the label, and then label will be translated into offset. Yeah. Yes. So that you always, like, regardless of where you jump to, you always link it to the next address. Yeah. All right. So if you have more questions, we can answer it later. So that's it with the control flow. Okay. Just pay attention to, again, to the nuances. And as I said, this is because we also might have 2-byte instructions, which we're not gonna talk about. All right, so another thing that I want to talk about is this notion of what we call pseudo instructions, okay? So far, the instructions I told you, these are all instructions that exist hard-coded into hardware in RISC-V, okay? But now, let's say, for example, I need to have more instructions. For example, someone asked that, why do we link when we don't need it? So why RISC-V doesn't have, like, just a jump instruction that doesn't link? In fact, it does. That's what we call a pseudo instruction. The pseudo instruction is an instruction that is not really hard-coded in hardware, but it can be easily translated into an instruction. So for example, like we have something like load immediate called LI, okay? Which what it does is that it loads this value into this destination register, right? So for example, you want to initialize your register 1 with 5. So you can have this. We don't have this instruction actually in the hardware. What we have is, for example, you can do add I, x, for example, let's say this is x2, x2, x0, and constant. These two are functionally equivalent, but this one is much more intuitive, right? So if you see this one, you say that, okay, I'm loading an immediate, but I don't need to provide another instruction for this. Instead, I can reuse an existing instruction. I just need to do a little bit of trick, okay? Why do we do that? Because we have limited space in hardware. We cannot assign so many instructions because each instruction needs an opcode, needs to be translated, needs to be decoded, and so on. So we want to have minimum amount of instructions that works and does everything we want. For example, another thing that you notice is that we only have 6 different branches, but we have things like, what if we want to do greater, not greater equal? So what should we do? You actually can build a greater with greater equal and other things. So you can actually build other things which we call pseudo instructions based on your current instructions, okay? So this is a list of like some of the useful instructions. So we have things like li, we have move, we have not, we have negate, we have actually jump that just jump without linking. We have call, we have jar, we have return, we have a bunch of different branches. And all they do is that they will be translated to other instructions, okay? So you can actually see from the list that I gave you already, you can build all of these things yourself. Question? You can write this at the compiler level, yes, and it will be translated. So this is what's called pseudo instruction. So compiler understands it, but hardware doesn't. So what happens is that this will be handled by the compiler into an instruction that hardware does understand. Again, this is convenience because, for example, let's say you've written programs in ARM. And ARM, for example, or MIPS has this move instruction. It's very handy. And now you want to do move in RISC-V and there's no move. You're going to be very frustrated, but there is option. Yeah, question? Yeah. No. So the question is, if I write this in assembly, what will happen? So these are still 4-byte instructions. Everything is 4-byte. They will be translated into either another instruction or maybe 2 instructions in some cases. So it might not be the most efficient way of writing things this way, but it's kind of convenience versus efficiency. Yeah. Mm-hmm.
I have one of these instructions which is because it's going to inflate that instruction 4-byte instruction, now an 8-byte instruction. Does that be able to get
True. So so the question is that if I have, so we're getting to corner cases, which is interesting. So if I have like a jump instruction here, and I have a bunch of instructions, one of which is a pseudo instruction, when I'm calculating the offset, what happens? So first of all, if I put label, and my label is somewhere here, then since this is compile time, it will understand it. If you put immediate, then you might have a bug. So you have to be careful about this. Okay, so that's kind of like the what you need to pay attention to. That's why it's better not to write things either pseudo instruction or knowing exactly what happens with your pseudo instructions. Yeah. So the question is, are we making instructions kind of complex? Yes and no. These are still really one operation, so it's like a not. But yeah, maybe for doing not, maybe you need to do an add and subtract. So it's kind of a gray area in that sense. But when we say CISC, it means that it's like really complex in the sense that you have the two very different operations at the same time. Yeah.
So like the general thing.
Uh, People do use it. So the question is, should we use it or not? And the answer is yes. Yeah. But also the question is how often you're going to write assembly instructions. That's a separate story, right? So like not many people will actually write assembly instructions. The whole purpose of this for you to understand kind of transition from software to hardware at the end of the day, rather than kind of like, training you to write an assembly instructions. We're gonna ask you to write, and then the purpose of that again is to understand, because understanding like this nuances will help you to understand the underlying hardware. Okay. So pay attention to this, and then you will have these tables. My suggestion is like take a look at each instruction, try to see if it makes sense. Uh, you can also practice and see if you can actually create the actual instructions from this. But most of them are fairly straightforward. Uh, so I want to particularly single out return and call, which are the two instructions here, because you're going to use this a lot, because return and call is like very regularly used, right? So how does this call and return works? Uh, so essentially call, what will happen with call is that you're going to change the PC to the beginning of a function, right? So whatever your function starts, you're going to change the PC to that. And you want to also remember where you call jump from, right? So you want to link that address of the current PC. So current PC plus 4 is linked to some register. Usually we call it return address register, which is actually just a pseudo name for one of the existing registers. It's not a new register, okay? Uh, um, and then when we get to return, what we do is that we really jump back to this address, right? So we kind of do jalr of this address, and then for return we no longer need to link, so you can actually do like x0 and then jump to that address, right? So that's kind of like what we do, and then the offset to this would be 0, right? Uh, so that's kind of like what we jump back to the return. Again, like if you look at this, essentially what it does is that takes the address of what we store in that return address. And again, return address could be any register. It could be x1, x2, x3. It's not a specific register. And then we jump back to that. And since we are using lots of function calls and returns, that's what we do all the time. Okay. You can actually practice this question and then have a quick break after that, and then we're gonna come back at 1:05, continuing this. Okay. All right, let's continue. All right, anyone wants to say what was the final number for this? Xn is what? 0. Anyone else find another number for this? We're good? All right, can you post, or someone post the answer to the campus wire so people can see how it works? Does anyone have any question about this particular example? All right. All right, so continuing on the calling convention, I also want to say quickly talk about calling convention as well. This is kind of less relevant to the design of the hardware, but typically we follow a set of rules when we are doing the call and return. The reason for this is all those things that you already said, that, oh, what if I mess up the return address? Where do I know where the kind of start address is? Where is my like return values are stored and all those things. That's why we usually follow a very, very specific guidelines when we are writing our assembly codes. And compiler typically follow these guidelines when you're actually compiling your C-level or high-level code into an assembly, okay? So the major rules is generally these three things, that the callee, so we have a caller and a callee, right? So the caller is like the function that's calls something, and the callee is the one that's being called, like main and foo, okay? So the callee usually promises to make don't touch some registers, right? So for example, the ones that stores the return address or maybe some like local variables and so on, they should be untouched, right? So for example, if you link something to, let's say, x1, which is typically what we call return address, the function that we are using, if it's mess up with this number, then everything will break, right? So we need to save that. If we really, really, really need to change them, we have to save them, push them to the stack. At the end of the call, we have to pop them from stack, recover them from stack, and then move forward, okay? So you technically can change them. There's no error associated with it. But if you do, you need to kind of recover them, okay? Another thing is that to make absolutely sure is that usually on the call, we push the return address into the stack. And then there's also like other things such as the frame pointer and all those things that is also being pushed and popped. I'm not going to talk much about the frame pointer and all those things. These are kind of more of an operating system problem, like where the stack is, where the heap is, where the code section is, and all that things. That's a separate class. If you don't know much about them, don't worry. We're not going to use it in this class either. All right. There's also like usually the stack. There's a calling convention on the stack. So typically, what we do is that the caller put the arguments that it wants to pass on into the stack. So if you have a bunch of things that we want to pass to a function, we push them one by one into the stack. And then we invoke the call instruction. We call the function. The callee then saved all the reserved registers into the stack one by one to make sure that they're not being overwritten. Also, like any base pointer, frame pointer, everything will be saved. Then it will kind of like reserve a room for their own locals, right? So we usually like move the stack pointer all the way down or all the way up, depending on like how the stack actually grows. And then we start doing things like pushing and popping things for our own local variables. And then once we are done, then we start restoring things, and then we're returning, right? So again, like if you think about stack, is that if this is main, we're going to push things into the stack one by one. So if this is our stack, like our stack pointer going to like go down. So my stack going down, but the other stacks could be going up. And then at this point, this would be the stack pointer that we call the function. Then the function will then push some other things, including like the return address, the frame pointer, and all these other things here. Then here would be where the local variables will be stored. Typically, when we get to this point, we push the stack pointer all the way down to here. And this is where we're going to store all the local variables. And then once we are done, we basically kind of reverse this process. So we're going to push the stack pointer up here. We're going to read these values and pop it from the stack. And then we're going to push the stack pointer here. And that's where we're going to pass the control back to the main. And again, this probably have seen this in CS33. How many of you are familiar with this? Like, how many of you haven't seen this before? Okay, good. So if you haven't, again, don't worry. You can take a look at your CS33 class. if you didn't, you're not going to see it again. But it's important to know that this is how we assume that we're following a calling convention. So hardware is not responsible for any of these checks. We assume that the programmer follows this calling convention. We're not going to check at the hardware level whether you have overwritten return address or not. And we're going to just pop and jump to whatever return address is showing. And that's actually the reason that we have what we call security problems, like buffer overflow problems, because hardware has no understanding of the context of the function. It just jumps to whatever address that you provided to. So if the malicious, for example, adversary can change things, they can override the stack, they can jump to other addresses and all those things. So that's the kind of like the root cause of many security problems, unfortunately. Another thing is that, as I said, there are some registers that are saved, and there is also in RISC-V, we have symbolic names for some registers. So pay attention to these symbolic names. X0, we call it 0. So for example, if you see some instruction like this, that X1, 0, and let's say add I, for example, and 4, this means that X1 is equal to X0 plus 4, okay? So name 0 means X0. Name RA means X1. SP is X2, is stack pointer. The global pointer is X3. The thread pointer is X4. Then X5, X7, and X28 to X33 is T0 to T6. These are temporary registers. These are registers that the callee can use for doing various things. Save registers are these two, are S0 and S1. X9 and X8 is the registers that you don't want the callee to touch, okay? And then the arguments, the function arguments and return values are stored in these registers, which is X10 all the way to X17. So we show it as A0 to A7, okay? So again, for example, if I do something like add, if I do add SP T0 A1, this is still same register. So we're not introducing new registers. We just use their symbolic names, okay? So you can always refer to this table to see the symbolic names. Why are we using symbolic name? Because it makes it easier for keep track of things. So you can always know that stack pointer is SP rather than always remembering that was it X1 or was it X2 or was it X3. So it's again, it's just using meaningful variable names rather than doing like random things. And this is also convention that you should use as a software developer, right? So you should use meaningful names for your variables. So the same thing applies to the assembly language as well. That we typically follow this. So you're going to see a lot of these in many of our examples. So if you see, for example, A0, that means that particular register. You can always come back to this table, okay? And as you can see, the savers are callee or caller or none. So this is like where one of them should be saving things and the other one shouldn't touch it, okay? Questions? Yeah. Uh-huh. Uh-huh. Sure. So the question, so the question is about like I gave you an example of like we're writing things to x2, but here I'm saying that for example x2 is your stack pointer. So why we're doing that? So these are like demonstration examples. They're not. So if you're in the context of an actual example, like an actual program, you should follow these conventions. That's the right way to write programs. So for example, if I want to write an assembly program to let's say some numbers, okay, like compute the sum of these like 5 numbers. Then you might wonder that, okay, which register should I use? Like, should I use X1 or X2? This is where you're going to follow this, right? So you're going to use like temporary registers, right? Where is my input? Your input is like in A0, or where should I return this to? And then those things, okay? So in like a good program, you should follow this pattern. So you should always write to T0 and T1 and so on and so forth. Yeah. So who defines this? This is kind of a standard in RISC-V. So So it's just a standard that people in RISC-V organization comes up with. So that's why I told you at the beginning that in order to connect the software world with hardware world, we need some form of a standard. So this is an actual document. This is a reference manual for RISC-V that has these definitions. There's no reason for it that why is it x1 that is a stack pointer, why is it not x3? Could be x3. It's just the only thing that matters is that it should be a consistent number that everybody knows so that you can follow that way. Yeah. No. Yeah, there's nothing special in any of these registers. Yeah. Is there any difference between A0 and A1 or S0 and like, no, there's no difference. So there's just numbers. So you have these 8s, you can use whichever you want.
But like, is there a reason separated?
Yes, the reason is like you usually, so the question is why because A0 and A1, we usually use it for return values as well. So if your function is returning only one value, that would be A0. If it's returning like 2, it would be A0 and A1. There's no more than 2. If you returning more than 2, then you have to provide it into the stack. Yeah. So the question is if I compile this. So first of all, compilers typically follow this convention. So if you actually compile a code and see the register, you will see that it's actually following this. So that's actually the role of the compiler to follow this convention. If you're writing it yourself, then you have to either follow this. If you don't, you have to be consistent in your program. Again, they will all run similarly in hardware at the end of the day. If you follow it with other conventions, so for some reason say that I hate this, I want to create my own table, you can write your own program and you can run it to your own program. It will work as far as you're consistent with your definitions. All right, so there's also another definition that I want you to remember, and that is kind of like the data sizes. So in RISC-V, char is 1 byte, short is 2 bytes, int is 4 bytes, long is 4 bytes, and so on and so forth. So just pay attention to this as well. And if you remember, we also called this word, okay? So this is also called word. Yeah. And then this is called double word, right? So this is double word. Right? So yeah, that's kind of like all the instructions that you need to know in RISC-V. So this is all the ALU operation, memory operations, and control flow operations. You have them all in this table. You have it handy. You can always refer to this table. Okay. If you have questions, feel free to ask on CampusWire, and we're happy to answer. All right. So now we have our assembly. Now we know how to write assembly. Now we know how to follow specific guidelines. Then what should we do? What we should do is that assembly is not something that hardware will understand. So we need to translate this one level further. Remember, we start with like a high-level C language. We translate it into this fairly complex assembly language, but this is still not enough. We need to go one step further, and this is what we call a machine code, which is basically unreadable if you don't know anything about it, right? It's just zeros and ones, a sequence of zeros and ones, okay? In order to transfer from ASM to binary, we follow a very simple table. So essentially, there is a table that tells you that if this is the instruction that you're using, this is the equivalent binary for that. How do we create that? Would be something like this. For example, for OR instruction, we have this sequence called opcode. We have this RD. Remember, like OR was like something like this, right? So it was like X2, X1, and X0, okay? So this was your RD, this was your RS1, and this was your RS2, right? So essentially what you need to put here is the number for RD. So you need to put 2 here, of course, in binary format. Then this is something else that we're going to talk about later. It's called func. This is RS1, this is RS2, and this is another thing that we call func7 that I'm going to talk about, okay? So for example, for OR, we're going to have something like this. So we're going to have like all zeros. We're going to have 0, 0, 0 here. We're going to have 0, 0, 1 here, 1, 1, 1, 0 here, then 0, 1, 0 here, and then 0, 1, 1, 0, 0, 1, 1 here. And this is also all zeros. So this would be a 32-bit version of this OR instructions, okay? There's a table for it. I'm going to actually break down all the kind of like components of this table. What I want to show you here is that this is how it looks like, right? So you follow a table. There's a clear instructions of how you should do every part. And then that will give you a 32-bit number, which is all zeros and ones. And that's what we're going to load into the hardware, and hardware will understand that and run that, okay? Yeah. So the question is, yeah. So this, by the way, this is the 31st bit. This is 0 bit. So it's from left to right. So the first 7 bits is the opcode. Yeah. But we can show you how we actually. So we need to dissect this into so we read this in parallel. Actually, we don't do like sequentially. We read everything in parallel. But that's the story of next week. All right. So this is how we're gonna do this. So first of all, we're gonna have kind of 6 different types of instructions in RISC-V. We have R type, I type, S type, B type, U type, J type. The types is really just the way that we kind of create this kind of table. For example, all of your ALU operations are R type instructions. All of your like immediate operations, those like ADI and I, are all I type instructions. Most of your JAL instructions are J type and so on. You don't need to memorize any of these. It's just a logical way of separating these things into these groups, okay? But the main thing is that you're not going to see more than 6 different groups, right? So this is all the possibility that you have, okay? As you can see, all of them are 32 bits. So starting from bit 0 to bit 31. That's one thing that you see in common. Another thing that you see in common is that the first 7 bits are the opcode. Opcode is essentially just the operation code. It's kind of like shows what this instruction is going to do quickly. And the important thing about opcode is that once we show you the hardware, we need to first know which instruction is this, because different instructions needs different operations. Like add needs to read 2 registers and add them together. Memory needs to read from memory. So the fastest we can know which instruction is this, it will help us to actually run this as fast as possible. And remember, the main thing for us is performance. We need to design hardware as fast as possible. So anything that can simplify that kind of process is what we are looking for, okay? So up to this point, all of them are doing exactly the same thing, 7 bits. Why do you think we need 7 bits? Why not less? Why not more? Yeah. Let's answer this, and then I'll answer your question. So why 7 bits? Yeah. Exactly. So if the total number of instructions that I have, if I take the log 2 of that, that will give me 7. Okay. So I need 7 bits to show all the instructions. I don't need more. I cannot do less because I'll miss some instructions. I cannot do more. And that's why now you understand that why it's really important to have limited number of instructions, because if I have many instructions, I needed more bits, okay? So here I only need to at most 2 to the 7 different instructions. That's the maximum of the instruction that you can support in RISC-V. If you want to go more, then you have to completely change the whole design. And this is more than enough, okay? So now question. Mm-hmm. So this is 5, right? So it's not 4. 5 bits. So 7 to 11 is 7, 8, 9, 10, 11. So 5 bits. So that's exactly why, right? So now we are actually going forward. So why we need 5 bits for register? Remember, we had 32. So log 2 of 32 gives you 5 bits. And that's why you have 5 bits for RD. You have 5 bits for RS. And you have 5 bits for RS1 and 5 bits for RS2, right? 32 registers. You need these numbers, okay? So now that we have actually answered all those questions, that's great. So now let's pay attention to another big thing, and that is your immediates. As you can see, immediates are kind of like scattered all around, and different instructions has different types of like immediates. The most kind of, so first of all, R-type instruction doesn't have any immediates. Remember, for example, add x1, x2, x3 doesn't need an immediate. So you don't need to kind of waste your space on R-type with immediates. So, so many instructions that doesn't need immediates, they don't use immediates, okay? But these all other guys are using immediates. I-type instructions has 12 bits of immediates. That is here. So the biggest number that you can show is 2 to the power of 11, like 2 to the power of 12 minus 1 if it's an unsigned, or 2 to the power of 11 minus plus that, right? So if it's like a signed version, then you have half on the signed version, on the plus side and half on the negative side. If it's just like you want to show unsigned numbers, that's the maximum you can show, okay? Why is it 12 bits? Because I don't have any more space, okay? That's the only reason. That's why I don't have enough. What if I want to do bigger immediates? I need to do twice, okay? So that's or multiple times. Then we have this U-type instructions, and these U-type instructions are actually have much, much larger immediate. And then pay attention to the kind of like this kind of combination of I and U. As you can see, it's like this one is 12 to 31, and this is 0 to 11. So that's how we can actually do this trick. So you can actually add some upper immediates and lower immediates together this way. So now I can really have like a full 32-bit if I want to. Then there's a bunch of others. So for example, this one, this S-type, what it does is that it has a same kind of size of immediates, but the immediates kind of broken down into 2 pieces. The reason for this is that if you look at the S-type versus I-type, I had 2 options, right? I could have had all the immediates here. In that case, I should have moved this RS1 to here, right? RS2 here, sorry. But what I did is that I moved the immediates here because generally it's easier to combine the immediate numbers together than reading the register. For register file, I need to have a quick access. So it's, again, a design decision. Next week, once I'm showing you the microarchitecture, you will understand why we are making these decisions of why we are moving things around. But technically, I could have like something like RS here and immediates all the way here, okay? Again, nothing different. It's just convenience for making things faster. Yeah. Mm-hmm. Then you use I-type. Yeah. So the question is, what if your number is less than 12 bits or smaller than 0 to? Then you use I-type instructions.
Like a bunch of zeros or a bunch of ones.
Yeah. Yeah. Mm-hmm. Yeah. Yes, I'm gonna get to that. Yeah, so let me see if there's anything else I want to show. Oh, so there are other tricks that we kind of use here. So for example, I use 1 bit weird here and 1 bit weird here. So the reason for this is that this is my sign bit, and what can I do with this is that the most significant bits I can quickly read it and gonna give me the sign, and this is kind of like the most significant bit of the immediate. For branch instruction, this is useful because I can branch to other places. And again, I'm going to show you the microarchitecture, and then your project 1 will be all about kind of designing the microarchitecture. There, you're going to actually look into this table, and you hopefully will realize that why some of these decisions are made and how it makes things faster. But I'm going to post some readings for you as well to see. But generally, if you see that the reasoning that we moved some of these things around is just because to make the hardware more simplified and more faster, okay? All right, so now somebody asked, what is func3 and func7? And func3 and func7 is something that we're gonna use for our R-type instructions, okay? Let me see, yeah. I think I have it here. Okay, so I'm gonna get to it. So here's the kind of the full table of all those instructions that I show you, and you can see that how they're kind of mapped. So these are the opcodes for some of these instructions. These are like different immediates. As you can see, for example, we are not talking about U-type instructions at all. So yeah, actually we have one here, the LUI. So you see that, for example, this is J type, this is B type, this is B type, this is J type, this is U type, this is R type. Sorry, this is R type, this is I type, and so on. So we have all the types here. Okay. So let's talk about each one by one. As I said, I already talked about immediates. As you can see, immediates are kind of different sizes and different shapes at different places. And mainly the reason for it is to make the hardware easier to understand this. Then we have this func3 and func7. So func3 and func7 is for giving you additional functionality when we are designing hardware. Okay. So as you can see, not all of them has this, and only R-type has both func3 and func7. So the way it works is we have this R-type instructions, okay? So if you look at XOR and look at sub, for example, you see that their opcode is exactly the same, okay? The opcode of this and the opcode of this is exactly the same, okay? Why? Because both of them are kind of ALU operations. I don't need to generate new ALU operations, like new opcode for each one. It's going to take a lot of time. The trick though is I'm going to show the difference between them in this func3 instructions. Like this is the func3, okay? As you can see, the sub instruction has func3 of 0, 0, 0. The XOR has func3 of 1, 0, 0, okay? So the ALU will understand the difference between these two by seeing at this second one. So essentially, we're going to kind of like populate this in 2 steps. And again, once I'm designing the ALU for the microarchitecture, you will see that why is it important to first know that this is an R-type instruction first or I-type instruction first, and then I'm going to see which operation exactly is this. Is it an XOR or is it an OR? Okay. Last thing is that func7. So in fact, in some cases, this is not enough because we don't have space. So we actually have this kind of unused space here, and we're going to use this to kind of differentiate things. So as you can see, for example, add and sub, they have exactly same opcode. They have exactly same func3, but what they have different is there's 1 bit in func7 that is different. So this is kind of telling you that whether you should add or you should subtract. Okay. So questions? Yeah. Yes. So func3 and func7 is giving you the arithmetic operation. Like, what is the functionality that you're going to see? The reason that they call it func3 and func7 is that 3 bits and 7 bits. Okay. So you have a total of 10 bits to tell you what to do. Yeah. Yes, so ALU is a separate unit. I'm going to talk about that actually next. So there is a controller that kind of finds out what you're going to do, whether you're going to do an ALU operation or a jump operation or memory operation. That's where we're going to see only the opcode. But then the ALU now needs to know which opcode, right? What do you want to do exactly? And that's where we're going to check func3 first, and that's where we're going to do a bunch of things. And then if we need be, we're going to do the func7. Someone else had a question here. Did I answer it? Okay. All right. So that's the story of func3 and func7. There is also other nuance and small things that, for example, there's this amount of shift that you need to add to the system. So this is only for shift left and shift right. This is just like an immediate that you use to jump. So for example, whether you're gonna, this is kind of telling you whether this is an arithmetic or a logical or yes, it's whether it's arithmetic or logical basically. Okay. So this is again, it could be 0, 0, 0 or 0, 0, 1 and so on and so forth. So it's kind of like similar to func3 when we call it a different name for it. Let me see if there's anything else. Yeah, that's pretty much it. The rest is really just have to look into the table and see which instruction is which and how we do it. That's all. There's really nothing like unique or very specific about this other than this. Okay? Any questions, final questions about the table? Yeah. We have 32, right? So log 2 of 32 is 5. All right. So again, you're gonna see this a lot in your first project. So you're gonna actually need to like have this table literally in front of you and then try to code this into your simulator. Good news is that we won't do all of this. We're gonna do only a subset of them. But anyway, okay. So if you remember, this is the slides that I showed you a long time ago that in order to build an ISA and run it in hardware, the first step is translating a high-level language into assembly. And we show you how to do the assembly. Then we now know how to generate this assembly to a machine code. We essentially follow this table and generate the binary code. Now the final two questions is that how to upload this into the hardware and how does the hardware actually run this? And that's kind of like the story of the next few weeks, okay? So first of all, how do we actually upload this? Remember I told you that we have what we call a store program order. So essentially what happens is that once I have this sequence of zeros and ones, I literally copy this into the instruction memory of my hardware. And that's what we're going to load this program technically into the hardware, okay? And in order to run this, all I need to do is I'm going to tell the operating system that change the PC to beginning of this code, okay? So the process of running an application in operating system is telling the operating system to change the PC to where the beginning of this application is, okay? And after that, it's just running this application one instruction at a time. If there are control flows, follow the control flows, and so on and so forth. Once it's done, it's technically returned back to the operating system, and the operating system continues this. Okay, that's really what is happening in your hardware. Okay, so this is how we're going to run this. So essentially, we store programs in the memory. We run things in the memory. We kind of like go step by step. And as I told you that there are other alternatives. This is what we call data flow. We're going to come back to this very, very late in the class in week 9 or 10. Okay? So this is kind of like to have a kind of like a flow graph picture. Your program using ISA will be an assembly. You will have an assembly to machine code. Your machine code will be loaded into the memory. You will have a PC, a program counter register inside the CPU that points to the beginning of this memory. And after that, you just run these instructions one at a time. Okay? That's kind of the timeline of an instruction, right? This is a few kind of like, links for you to look into these tables that I grabbed. So there are a bunch of good ones that you can look at. I just provide the sources for you. Important thing is that we didn't cover RV16 and RV64. These are 64-bit version and 16 version of RISC-V. As I said, in this class, we're going to just focus on the 32-bit version. 32 version itself has other extensions such as M and A and others. We're going to only focus on the base one, okay? The base one, which is we call I, okay? So those lists of instructions that I show you is only a subset of all the instructions that exist in RISC-V, okay? There's also floating point instruction and register that we're not going to talk about. There's also privilege instructions, P version that's kind of talk to the hardware and or talk to the operating system that we're not going to talk about. Okay. So essentially, one thing I want you to remember is that there are some other instructions in RISC-V that we don't talk about in this class. We just focus on the base version. Okay. And this is generally for writing like a general purpose program. All you need in this class would be enough, but there is more to it as well. Okay. There's also other types of instruction set architectures such as VLIW, very large instruction vectors, and CISC, and microcoding that we may cover if we have time, but in most likely we won't. Okay. All right. So that's it with this part of the lecture. I think I can. Let me see what I have. Let me give you like one quick thing for the microarchitecture. We're going to talk about it next time. So this is kind of like the next module that we're going to talk about next week. So essentially the question is that, okay, I have this binary, I have this instruction set architecture. how do I design my hardware to run this? Okay. This is what we call the microarchitectural design. This is the implementation of a given ISA is what we call a microarchitecture, okay? And as I told you, for a given ISA, we might have different microarchitectures. For different version of a microarchitecture, we might have different changes, okay? So essentially, the microarchitecture that we're going to talk about is going to look something like this, all right? So you're going to have what we call a data path and a controller. The black part is what we call a data path, and the blue signals is the controller. In the next 2 weeks, we're going to break down this fairly complex design and all these wires, and we're going to explain why we have this. One thing I want you to look at is that it starts with the PC and your instruction, and you can see that how your instructions kind of divided into multiple pieces. We have register file, we have the immediate generator, we have our ALU, we have our memory, and so on and so forth. So there are these all components that we connect together in order to build this, okay? So we're going to talk about that. And the main thing that we are doing is we want to make sure that our system is efficient. So all the design decisions will be based on efficiency, all right? So last question, I'm going to let you go. The question is why B-type put the 11th on the other side. It's because 11th and 12th give you the sign and most significant bit. And this is useful for branch predictor. We're going to talk about it later, that how we design the branch predictor. All right, guys, thank you. Homework 1 is out, so start working on it, okay? And we have class today for the honor section at 2.